Thank you, everybody, for attending. We're here for our inaugural Microgrid Innovations Research Center workshop and student research showcase. I'm Douglas Van Bost. I'm the director of the center, joined by many of our center members here today. We've been a center officially now for a couple months, but we've been working together for about 6 years. So before we go too far, Commander Thomas asked us to make sure we flash this up on the screen. The foundation provided the food. Federal workers were allowed to accept up to $50 calendar year. There is a basket out there if you would like to put money in it for any particular reason, as they state up here. Okay, so the mission of our center here is to support Department of Defense energy resilience needs through accelerated microgrid technology research, development, and transition to critical applications. We feel very passionately that energy is very important for military operations. You've probably heard recently phrases such as energy dominance. That is true. That is what we're trying to do. We make sure we have the energy that we need on the battlefield to be able to do our missions and also at our bases. The center is comprised of faculty, staff, and students, many of which are here today. And thank you for all the students who we twisted their arms to come and present their research. We really do appreciate it. If you want to get involved, you're not currently involved, there are many opportunities to get involved. For students, lots of opportunities to do thesis research, capstone research with us across just about every single department in the university. If you're faculty or staff, there are ways that you can come and work with us on joint funding and on projects we already have funded to support the work. Our successes already, we have our first pilot microgrid being commissioned next month at Naval Air Station Sigonella to support one of their critical loads, with 2 more to follow there in short succession. And in terms of students, we've graduated almost 100 now with the center. And we've received over $7 million in funding over the last 6 years to support all of our efforts. In terms of naval impact and naval relevance, what we are trying to achieve is that energy dominance and energy security, especially from the perspective of energy resilience. So energy security has 3 pillars. It's reliability, efficiency, and resilience. We understand reliability, make things more reliable, improve their function. We understand efficiency, turn off the light bulb when you're not using it, put in LEDs instead of old incandescents. Resilience is harder. That's what we've been working on for the last 6 years. Another major impact we've had is the microgrid planning tool, which Dr. Daniel Reich has been the lead in developing. This tool is now in use by NAVFAC installation energy managers across the Navy to help with designing the early phases of microgrids that then they can go and get funding from NAVFAC to be able to actually build on their bases to improve the base infrastructure, improve energy resilience. And more recently, we have developed zonal nanogrids, which are based on zonal shipboard power. So those of you that have been on more recently constructed ships probably have had some experience with those systems. We're bringing that to shore. We're transitioning that technology into our bases. That helps to make sure that our bases will have power on the critical loads when and where they need it in spite of whatever is going on, storms, adversary action, whatever else. And this just gives some of the statistics of what we've been up to. In addition to the funding and everything else and the students graduated, we've produced almost 40 different journal articles and conference papers published in peer-reviewed venues. And out of those 100 students, that equates to 41 theses, capstone projects, and dissertations. And with that, I'd like to hand it over to our first student. And students, remember, 4 minutes each.
Good afternoon, everyone. My name is Lieutenant Andrew Cho, and I'll be presenting to you on the FPGA-based virtual twin testbed and design implementation of zonal nanogrid system digital twins. So that's me. And it's a lot of words, so I'm just going to define the terms a little bit, right? What is a zonal nanogrid? Well, a nanogrid is a smaller microgrid, and a zonal just means that there's a compilation or a multiple nanogrids that are in conjunction, and they support each other in a system. What is a digital twin? Well, a digital twin is a concept that incorporates a virtual and a physical twin. And so it can be implemented in any system, and the physical and the virtual twin will fully represent each other, and it can be utilized for fault recovery or forecasting, optimization. My thesis will be specifically based for the virtual twin portion that will eventually be implemented into an ultimate digital twin of a zonal nanogrid system. All right, so how did we create the virtual twin testbed for the zonal nanogrid system? So here is the design process for us. On the left, you see the computer side, and on the right, you'll see two magenta boxes. These boxes are the FPGAs. So on the left, starting from Simulink, so we modeled all of our nanogrids on Simulink first. So you can see different boxes here, which are the models that we created. So we have the power electronics model, the BESS generated PV, and then some of the communications models. These models are then run through what's called an HDL coder. This is an internal thing in Simulink that produces HDL code. And for us, we used Verilog to be instantiated into Vivado. So all these models are going to be converted to Verilog, instantiated into Vivado, into what's called a nanogrid project for us. This nanogrid project, within Vivado, we incorporated what's called the coordinating EMS, so the energy management systems for our FPGAs. And then that Vivado will then create the code that's being instantiated into our FPGAs. So on the left, you see the FPGAs, and these are running in real time. All the models that we created in Simulink are then implemented into our FPGAs, and they're being run concurrently. The serial comms model, that's going to be FPGA to FPGA communications, and the USB UART comms model sends everything back to the computer to be run into MATLAB, and then we get some graphical analysis for that. All right. So how do we do this? As you can see, these are the FPGAs that we used, and there's two of them that we wired together. And it's being, for us, we ran it for 24 hours, and the results are being sent into the computer and being graphed. And you see the MATLAB graph on the left. There's a couple more to show, but this one is our battery state of charge. So we have two FPGAs right now, Nanogrid 1 and Nanogrid 2. Nanogrid 1, there's a generator that fails, but Nanogrid 2, there's no generator that fails right now. So I set it up so that the battery state of charge is in between 60 and 90%. Once it reaches 90%, our generator shuts off, the battery depletes down to 60%, and the generator turns on again. In the middle portion, you can see a little bit of the rate of charge change. That's because PV turns on. So PV is off during the at night, and then when the sun comes up, the PV turns on, and so you can see that changes. And then once the Nanogrid 1 depletes after generator failure down to about 10%, Nanogrid 2 sends power to Nanogrid 1, about half of its generator power, so 2,000 watts, and it starts receiving power. And you can see the rate of charge for Nanogrid 2 change after it starts sending power. And this is our current voltage graphs along with the power graph. If you want to look with me to the power graph to the generator, the green line on the bottom right, you can see that it's turning on and off depending on the state of charge of the battery that you saw previously. And also on the PV graph up top, you can see that the PV is off during nighttime. And then once the sun rises, this is actually a simulation for Monterey, California, by the way. So we brought this in from PV Watts, and during the daytime, the PV turns on. And then finally, you can see that the battery, right, this is Nanogrid 1. So once the generator fails, the Nanogrid 1's battery power only reflects the PV. And then once it starts receiving power again from Nanogrid 2, you can see that the power comes back up to about 2,000 watts when it's receiving power. Any questions? Yeah, I'm sorry. It's a lot, but it has to be quick. So do you have any questions? Yes. Yes, great question. We can honestly hook up indefinite amounts. So currently we have two. We have actually Jacob Burns. He'll be taking after me, and he's working on 3. But we can continue to bring it up. Just the limiting factor is the PMOD port on the FPGA. So there's 3 PMOD ports, but we only need 5 wires to connect them. So and each PMOD port has 8 connections, which gives us, I think, 6 connections that we can make. So if we have an option to connect it without using the PMOD ports because there's other ports on there. But if we only use PMOD ports, we can have up to 6 FPGAs connected. Thank you. Who's next? Yes.
Testing. Okay. Good afternoon, everyone. My name is Lieutenant Jorge Rivas, and I'll be going over a novel low-cost digital twin testbed for microgrid transition. For this project, Dr. Reedy was my advisor, and Dr. Sulasaraman is my co-advisor. So I have a quad slide followed by pictures. That way I can put a picture next to some of these things. So what is a network microgrid? Andrew did a great job at defining what a microgrid is. To further that, so we have several microgrids that I'm working with that are all each independent. I have them physically connected, so they are able to transfer power. Additionally, they're functionally interoperable. What does that mean? They're sharing data constantly, and they're able to act on that data by themselves. So the current setup, as I mentioned, so for hardware, there's a proprietary company that we're using that sells these microgrids. So I'm using that in addition to a Raspberry Pi. So this is maybe $100 tops for the high end, and then FPGA that Andrew was just talking about, and then software that I'm using to create this testbed is basically just Python and implementing 3 different protocols: MQ telemetry transport, which is an open protocol that's in the Raspberry Pis, in addition to clients. Clients being basically any computer that we want to be able to communicate to the network, and if you want to manually give commands, that's how you do it. You just use this program and you can send each of the microgrids commands. Modbus TCP/IP protocol, which is what is being used for the Raspberry Pi to talk to the proprietary microgrid, and then the universal asynchronous receiver and transmitter protocol. That's what the FPGA and the Raspberry Pi are using to communicate to each other. So why do I want to create this system? So there's several use cases. So as I have it right now, I have independent operation as a standard for each of these 3 microgrids. What I have them doing is, in case of an emergency, let's say that we have, and I named it microgrid 1, 2, and 3. Microgrid 1 goes down. Microgrid 2 will be able to take over and supply power to the load of that microgrid that just went down. How does it do that? Well, as the microgrid goes down, is able to, using MQTT protocol, is able to communicate to the others and say, hey, I went down, this is my current load. And the next one can read that and then both change its mode of operation to be able to be grid connected, and then also supply power depending on the load value that was there before. So it is able to do this all autonomously currently. Another thing is that these microgrids can also be incorporated with a digital twin concept that Andrew was just talking about for fault detection. So what we can do is we have the digital twins running simultaneously, and then if there is a % error difference in, say, the battery percentage, which is a known thing. Sometimes when you shut down a microgrid and you turn it on too quickly, the calibration gets kind of wonky, and then the battery may not properly display. So we can use a threshold to have the system basically say, oh, hey, there's a difference greater than my threshold at this point. Let's have the system autonomously go through different values, say like the battery voltage, the current direction and value, etc., to try to decipher what could be wrong with the microgrid. And also a recovery strategy. So as a lot of the digital twins are used right now, you can use them to kind of go through different models, different simulations before making a decision to make sure that that is the optimal decision. If we have several microgrids that have different size batteries or different, some of them have PV, some don't, we can use the FPGA as well to be able to go through different scenarios. And then for future work, another project I'm working on is using machine learning models for anomaly detection. So we can actually incorporate that into this system as well. And then company agnostic implementation. So right now I'm working with one company, but really any company could work. So the way that it's working, the Raspberry Pi has that proprietary communication going through that one company. But if we have one Raspberry Pi per microgrid, then it doesn't matter what company that creates the microgrid. They can all work together. And this is all done wirelessly, so you don't have to worry about any physical connections. Each of the Raspberry Pis are able to connect wirelessly to each other. They're generating their own wireless network. And then as promised, here's some pictures. So what was I talking about? The Raspberry Pi is that little thing right here in the black. Again, maybe $100 most. A lot of these systems, these digital twin test beds tend to be hundreds of thousands of dollars, depending on how in depth and how big it is. So this is just maybe $100, maybe 150 for the FPGA or 200, depending on what you're getting. And this is one of the microgrids from Outback Power Systems. And then you have the proprietary controller up there, and they're communicating via the protocols that I mentioned. And then scalability. So on the right here, you have 3 microgrids. Each of them are able to be connected to each other physically to transfer power, wirelessly for communication between the Raspberry Pis, and then also, as Andrew was talking about, there's a FPGAs running the simulations for each of those. These pictures were gathered from a paper that just got accepted to be published in the conference occurring in October. Any questions for me?
Hello, my name is Lieutenant Adam Stowe. I worked on anomaly detection in a microgrid using machine learning methods to enhance power security. So the purpose of my thesis was to help us transition from reactive or preventative maintenance to predictive. So as we detect anomalies that occur that could further develop into a fault that could cause extreme damage to the microgrid, we can detect the anomalies, say, hey, there's a problem, figure out what equipment it is, and then replace that equipment before anything else happens. All right, so the microgrid I used is currently on the golf course. It's a commercial off-the-shelf microgrid that was built for purposes of a deployment for a forward operating base. I used 3 modes of operation, as much more than that, but I wanted 3 distinct modes to test on. The first mode was mini-grid. This means that as the state of charge of the battery is depleted, the microgrid will connect to the grid in case of once the battery voltage reaches a certain preset point, and then it'll charge the battery all the way up to 100%. Transition back to the battery and the PV array. Also had grid connected, which means it charges the battery to 100%. Once it's at 100%, it only supplies the load based on the grid. And then generator connected, very similar, charges the battery off the generator to 100%, and then supplies the load from the generator. I collected data for 2 days on mini-grid and grid connected, but I didn't want to run the generator that much. So I used 4 hours of data for the generator. That was about 170,000 data points for those 2, and then 17,000 for the other. Then I used 3 supervised machine learning models to detect the anomalies that were input into the system. One-dimensional convolution neural network, long short-term memory, and then support vector machine. So the picture on the right, right for you, is the microgrid that I used. It's got an Outback system for the control of everything. It has 1 set of PV arrays charging the battery. It's got its battery bank, a generator that can or cannot be, or may not be connected with a controller, the Arduino controller, to turn it on or off. And then it's got a programmable load, and then a simple AC box fan also connected for the loading on. It's all the data is collected from a Fluke 434 power analyzer. And so what I was collecting is I collected the voltage, current, the real power, reactive power, power factor, and apparent power to detect the anomalies. So these are all photos of the data from mini-grid. I shortened on the time, so I wasn't going to go through all 3 different modes of operation. But these are some of the different normal operations that occurred in the system while detecting the anomalies. So some of them include battery recharge event for a mini-grid. So collected on that as a normal operation. With both loads running at the same time, and then only one load running at different times as well, collected for normal operation. The anomalies that were input into the system were as many of the 9 common power anomalies, as well as different tests to make sure it can detect a transition in the mode of operation that isn't supposed to happen. So if you're in mini grid operation and it connects to the generator, you want it to flag that it connected to the generator because it's not supposed to. So things like that, detecting those mode of operation shifts. So I have over voltage, under voltage, shifting to the generator. And then other than that, it was to detect as small power shifts as I could to correlate with like a load slowly breaking down. The load is slowly drawing less power. The components are slowly breaking down, becoming less efficient. That's what the fan speed shift and the lowering or raising the programmable load by 20 watts is trying to do. And then the simulating the different loads, the purpose of that was to make sure that it can utilize all of the power inputs into the system to detect an anomaly. So it's not just relying on voltage or current. It can see that real power is the same in the cases of the simulated loads, but reactive power, apparent power, and power factor are vastly different. So it'll flag those. So the results on it are as shown. The 1D CNN and LSTM struggled a little bit compared to SVM. And so the on the right is the average over the course of the 3 different modes of operation. The goal was to have accuracy and recall above 95%, and the precision and F1 score above 90. So this did occur for SVM, especially after I used a post-training smoothing, which instead of doing one data point at a time, it took a whatever it determined as the most optimal time period, fed that data through the different AI detectors, and then that would detect based on the different set of data rather than each individual data point. And then SVM almost reached that point with just the singular data points as well. Does anyone have any questions?
All right, good afternoon. I am Major Andrew McClinton. I'm a computer science master's student. I'm going to see if I can back up one slide just so I can lead that because it's a good transition. So the 3 models that Adam Stowe used for his research, the 1D CNN, the LSTM, and the SVM, were all created by a predecessor of mine in the computer science department for part of his research. Ultimately, my thesis took one of those, the 1D CNN, modified it to increase the performance of anomaly detection. And then I also incorporated Bayesian methods into it. So what I resulted in is a Bayesian neural network that is able to perform anomaly detection in power systems. Now, power systems, why not microgrids? Power systems mainly because what I have created is potentially scalable, and it is applicable to both microgrids and general power systems in general. All right, so breaking that down and moving straight into, I'll get this right eventually. All right, so what we're looking at here, microgrids and power systems in general have significant vulnerabilities, both to internal component delay or denigration, as well as cybersecurity threats. So there's a couple case studies out there where cybersecurity threats were able to get into a power system and disrupt how it functions, the power generation, and ultimately we're able to take it offline. We don't have any good measures to detect these anomalies or detect any kind of component delay or degradation over time. There's a couple different ways you can skin the cat. I took the 1D CNN model and I made some improvements to it. And most of my work was done utilizing data collected from this system right here on your right. So as you can see, it's got a couple fans in it. It's got a couple PLCs, power input up in the top left, and then the data collection methods throughout the system that allows it to operate as a simulated microgrid and then collect data in parallel. The data was collected at 10 hertz, and it generated, I believe, right around 500,000 data points with a total of 7 anomalies. So with that, I moved on forward into my developed neural network. So the big thing here, the 1D CNN model, the convolutional based neural network, essentially has these weights between the nodes. These weights are fixed. So as the linear math calculates and the data flows through the network, those can be varied through training epochs, but they are more or less fixed for per iteration of the model. So what I did was I shifted it so that it had a Bayesian component to it. And the primary difference is instead of fixed weights, you have a distribution of the data or a probability distribution across those nodes. So what that allows you to do is while the neural network, the base neural network allows you to have some uncertainty, it improves the uncertainty estimates. And that translates into better confidence estimates of whether you are sensing an anomaly or sensing normal, clean data. So these are the results of my research. On the left, I have the validation information in here. That is just a portion of the training regimen for an artificial intelligence model. What I really want to draw out, though, is the test information or the test results here on the right side of the screen. So basically what I was able to do was I was able to increase the performance of the 1D CNN model that Adam Schroeder created that was being used by Lieutenant Stowe. And without any post-smoothing or any other modification to the results, I was able to generate accuracy, F1, precision, and recall all approaching 1. So near perfect diagnosis of anomalies versus clean data. And not only that, but what this also showed was that when the validation was performed and the test was performed, the anomalies and the clean data that were presented to the model were completely unseen prior to. So the model was trained on a certain amount of data, a certain amount of clean and anomalous data. And then we showed it something that it hadn't seen before for the validation, and then showed it something else that it had never seen before for the testing portion, which basically means that this system or this model that I have developed is able to detect both known and unknown anomalies, which means it makes it a lot simpler for us to train a model on a microgrid, because as anyone who's worked with microgrids before, it's very difficult to enumerate the number of failures that you can see within the system and combinations and second and third order effects from those. So what this does is it allows us to say with 99% confidence that when an anomaly occurs, that the system is able to detect it. The one last thing I'm going to talk about before I get off the stage is the AUROC. So that is essentially, for those who are not familiar with it, it is essentially a test of how well the system is able to diagnose not only whether it is a clean or anomalous bit of data, but whether it has or has not seen it before. So the 95% confidence there shows that the system is able to say distinctively that I have not seen this before correctly, and then properly categorize whether it is anomaly or whether it is clean data. Do I have any questions?
Good afternoon, everyone. My name is Joe Kreis, and today I'm going to be talking about non-intrusive load monitoring. That was kind of my portion with the microgrid. So basically, non-intrusive load monitoring, or NILM, is when you use special sensors applied to a central part of the power system. From there, it monitors and observes that power load, the aggregated load of the system, and then using machine learning algorithms like Adam and Jorge are both doing. Individually, I'm using a sensor that the Army Research Laboratory gave us called the NPM. But basically, using its own machine learning algorithms inside of the hardware and its own sensors inside this little curved bed here. This is where you put the conduits, the wires, or the cables. That's what you're trying to measure. And then from this Ethernet port, you run that to a host computer to observe the data. But anyways, you use that to kind of diagnose power faults, anomaly detection, all the important things we just talked about. But this kind of robust system is what we're testing to hopefully be used on U.S. Navy shipboard systems for three-phase power systems. So it gives you three-phase currents, voltage frequency. So my part of the research is these have never really been tested before. We're trying to implement them for widespread use. And the first step of validating them is kind of ensuring that the data is correct. And the way that we did this was we used oscilloscopes. We made our own little three-phase power system here attached to the microgrid power system. But we have these three-phase motors here, attached different loads. And then we have our NPMs installed at various points, which we can corroborate with these oscilloscope current probes and the voltage probes there. Here's the schematic here. So basically we were just running through testing each NPM. Some of the NPMs, they are intended for three-phase loads here. You can see 3 different phase cables and these 3 NPMs, but in these 3, we just tested how they would do with just single phase currents and power signals. The results, I didn't make a slide for it, but they do pretty well at detecting behavior changes and stuff, but they were usually off in value by some scaling factor. So we think we need to do more testing with calibration issues. But yeah, this is just another step forward for bolstering our energy security. Are there any questions?
Good afternoon, everybody. I'm Ensign Ford Knippa, and I did my thesis on methods for estimating microgrid resilience for the DoD. My advisor is Professor Daniel Reich and second reader Daniel Eisenberg. And this work is a part of the microgrid planning software that he's working on right now. So just the research summary, we did this research on resilience, which we defined as the performance of a microgrid during an improbable severe disturbance. And our goal was to create methods that better encapsulate microgrid resilience than the existing methods. And again, we're going to implement these into Microgrid Planner. From this research, we had a couple contributions. The first of these was we proposed several methods for computing resilience, and we went through and developed test cases to test each of these methods on the test cases. They were different demand profiles that were simple enough to test the test cases and kind of anticipate what it would be, but yet also complex enough to where it reflects what we thought a feasible microgrid, what a feasible demand curve could look like for a microgrid. We then compared the performance of the existing methods to our proposed methods to determine which of these methods would perform well when trying to measure resilience for a microgrid that's in the process of getting planned. From our research, we determined that we wanted to compute resilience based on high demand time periods within the disturbance that experience a power deficit. And this was with the goal of avoiding overly optimistic resilience results. That's kind of what we observed from the prior metrics that exist right now. And then we average resilience values of a single disturbance event over multiple potential start times to avoid computational instability. So what this means is you have one disturbance event and you kind of move that around within the time horizon to test if it occurs at a time a little bit before or a little bit after, what's going to be the result. And we found that it could differ vastly between slight variations in the disturbance time. So that second bullet point at the bottom, we refer to that as time shifting. And so I created this slide right here. This is one of the most simple cases that we could construct for a microgrid. We have the blue demand curve. So low demand periods would be nighttime. High demand periods would be daytime. It's at 10% during night and 100% during the day. We have a really short disturbance, only 3 hours. That's in red. And that shows the supply. And the time of impact is that black dotted line. Time of recovery is the green dotted line. So that's our single disturbance. And then if we look at our shifted disturbance, this is that time shifting thing that I referred to on the last slide. We start looking at time 3, and then we can shift it 1 to the right, and then again, and then again. So we have 3 different disturbance scenarios that we can evaluate.
and we can get resilience metrics from each of these disturbances, and then calculate an average of these metrics to determine an overall like single scalar value. And we think that this will help a lot in creating more stable metrics. If you look at the disturbance on the right that's shifted, that third disturbance that we measure, it's entirely during the daytime high demand periods, whereas the first disturbance here does not affect the microgrid at all. And so by shifting this disturbance back and forth, according to a given amount of disturbance shifts, we can calculate much more accurate metrics. That's all I have. Any questions? Thanks.
All right. Hello, everyone. My name is Noah Wheats. I am a SC PhD student working on my dissertation, which is a systems engineering approach to resilient microgrid design for austere environments of interest. So I think we've heard a lot of honestly really great thesis topics and research that's being conducted. But as we look forward to where we're starting to put these types of microgrids for the warfighter, we have to think about the environments that we're most likely going to be operating in. Some of those being the Arctic Circle, Pacific Island chains, which are very remote, and then also looking forward into the future with NASA for the lunar surface. And so part of what my research is looking to try and achieve is, can we start to essentially develop better methodologies for how we can integrate resilience early during the conceptual design phase, so we can produce multiple architectures that provide different designs that can then be down selected for detailed design for further analysis, and hopefully yield a better microgrid architecture when all is said and done. So my research objectives currently are to just assess the different environments that I'm currently interested in, being the lunar surface, the Arctic Circle, and the Pacific Islands. Basically determine what makes those environments unique and develop some representative design reference missions and CONOPS for those, and then use the methodology that I'm creating to develop a handful of processes specifically aimed at the challenges that each of these environments pose. And then lastly, assess those processes by actually developing some architectures and assessing how they fare based on different failure scenarios that I've developed, as well as validating if those processes and the methodology end up hopefully producing what I think they will, which is a lot more resilient microgrid design architectures. So with that, kind of rushed through it, but any questions? Ready? Thank you so much.
Thanks. Well, let's give a hand again to all of our student presenters here. Thank you, everybody. And so for all of you that are interested in getting involved in this, now that you've seen this, especially all the students that are here, I know many of you are thinking about thesis topics in the future and what you're going to do. Please talk to our students that just presented today and also to the faculty that are here. For faculty and staff that are interested in getting involved, please also approach us afterward. We can definitely talk with you and give you the rundown on how you can get involved. We'd love to have you aboard. And to remind you why we care about all this, it's all about making sure we have energy when and where we need it in spite of whatever's going on, to make sure that we can operate the missions we need to. That's what the center is about. That's what we're doing with all these wonderful microgrids. And we're going to keep working on this to make sure that we have energy dominance. So with that, thank you, everybody, and make sure you get some food if you haven't already, and we'll all be here to continue talking with you.